Number 1, a student titrates 20 milliliters of 1 molar NaOH with 2 molar formic acid. So before we do the questions, which apply to the next 5, let's remind ourselves of language. If you're titrating the NaOH with formic acid, usually that means the NaOH is down here and the formic acid is in the burette. So, like that. Alright, now they want to know how much formic acid is necessary to reach the equivalence point. And there's a couple of different ways that you can do this, but what they're saying is how much of this liquid will be required to neutralize that stuff. And so the first way we're going to look at is the MV equals MV way, where this is acids and this is bases. Now you remember that even though they're giving us the Ka here, and you might be worried that formic acid is a weak acid, it doesn't matter as far as how much of the acid will be required to neutralize the base. If it's a titration question and we just want to know the concentration of one of the two of them or the amount that needs to be added, it is solved the same way, whether it's strong or weak acids and bases. Now the other thing I want you to look at before we solve it is, because they're not the same concentration, this one is twice as concentrated as that one. If it's twice as concentrated, it should take less of it to actually reach the equivalence point to have the same amount, because the equivalence point is the place where the moles of both are the same. So if this is twice as concentrated, we'd expect half as much to be the answer. So I think A, 10 is going to be the answer, but let's do the calculation. Alright, so 1, if we set up the calculation like this, and I'll let you actually do the algebra, if we multiply these two and divide it by 2, it does look like it's going to come out to be 10 milliliters. So the answer for number 1 is A. Now number 2, they want to know at the equivalence point, is the solution acidic, basic, or neutral? Well, if you're sort of forgotten one of the concepts, you might think immediately it's the equivalence point. If it's the same amount of acid as base, it must be neutral. But actually we can rule D out right away. That's definitely not the answer. It would be the answer if this was a strong base and that was a strong acid. But they aren't. That's a strong base and that's a weak acid. So let's draw the reaction out and see what it looks like. So here I've drawn the reaction, sodium hydroxide reacting with formic acid. That H is going to be the acidic part, that's going to be the base. They're going to get together and make water, and then you get sodium and the rest of this stuff. I actually prefer the net ionic equation version of it, where if both of those are going to be soluble, so Na is the spectator ion. And it's quite a bit clearer here. So hydroxide pulls the H off, makes water, and this stuff. And this stuff over here is, we like to think of it as a salt. But remember, salts can be acidic or basic. And because this one is an anion, as in it's negatively charged, it's definitely going to be basic. So why is it going to be basic? Because if CO2H- is sitting around and it has water to react with, it could, if it acts as a base, it could pick up that H and make HCO2H. In other words, go backwards. Plus OH minus. If it does this reaction successfully, it will make hydroxide and it will make the solution basic. So some salts are acidic or basic. In this case it will work pretty well because this is a weak acid, so we will get some progress this way. Now remember, compare that to if you had chloride minus ion as a product, well then that would be a perfectly neutral equivalence point, because when you try to go this way to make HCl, well, that's a strong acid, and there is no way that that reaction is going to go forward. So the answer to this one should be that the reaction is basic, and then we just got to figure out whether it's B or C. Well, if you look at B, B says it's basic because the only ion present at equilibrium is a conjugate base. That's sort of true. This is the conjugate ion that they're talking about. And if you look at C, it says basic because the higher concentration of the base is the determining factor. Well, that definitely is not true because it's at the equivalence point. The amount of base we added has to be equal to the amount of acid we added. So I would say B is going to be the answer to 2. Alright, number 3. If the formic acid were replaced with a strong acid such as HCl at the same concentration, how would that change the volume needed to reach the equivalence point? And so I've drawn the two reactions we're talking about. So we're adding base to formic acid and we get the reaction to occur, But if we're adding base to a strong acid, you notice that as long as the stoichiometry is 1-to-1, it does not change the amount of base that's needed. So the answer is it would be the same. Now, of course, the second one, because it makes chloride, would have a pH of 7 at the equivalence point, and this one wouldn't. It's going to have a more basic pH. So let's see what the answers are. A, the change would reduce the amount of no. The change would reduce the amount of base, nope. The change would increase the amount of, nope. Changing the strength of the acid will not change the volume needed. So it looks like the answer here is going to be D. Number 3, number 4. Which of the following would create a good buffer with the formic acid? So let's remind ourselves what buffers are. Buffers are whenever you have a weak acid and its conjugate base. It must be weak acid, can't be strong. So examples are HF, because that's a weak acid, and F-, that's its conjugate base. In this example, which is a common one, ammonium is the weak acid, and ammonia is the conjugate base. So if we were looking for a formic acid, well, formic acid is HCO2H up here. So obviously what we're looking for is something that is its conjugate base, which is where you deprotonate that ion. So it should be something that looks like that. Now you remember that it's always disguised because you can't have a negative ion by itself. It has to have a conjugate. So it could be potassium formate or sodium formate. And you can see that the answer is clearly going to be A, sodium formate. Hey, by the way, before we do number 5, in case you're wondering, I am on a playground, and that's why it's windy and you hear kids. So let's see, number 5. In which pH range would a buffer made from formic acid be the most effective? So you remember that for a buffer to be most effective, it should be high concentration, as in it's got to have high buffer capacity. And we'd like there to be equal amounts of the acid and the conjugate base so that we have both systems to absorb acid and base. And so we can think about it in terms of the Henderson-Hasselbalch equation. So remember that base goes on top, so in that case we're talking CO2H-, and acid goes on bottom. And if we have equal concentrations of these two, they're going to equal 1, and the log of 1 is 0. So this is going to be a situation where the pH is going to equal to the pKa. So if we have equal amounts, which is the optimum buffer situation, the pH will equal the pKa. Well, how do we find the pKa? Well, they gave us some information back here at the very top. The pKa is 1.8 times 10 to the minus 4th. And you remember that if you were to negative log this, and you do not have a calculator here, if you negative log it, the pKa is going to be about to the power, and the power is 4. So the pH is going to be about, or the pKa is going to be about 4, and so the pH will be about 4, but maybe a little bit under, so 3 point something. So I'd say the answer is going to be B.